Happy Tuesday.
We're good. Thank you.
We are starting the big theorems, big three. D is an open, simply connected region with a boundary curve. Partial D is a piecewise smooth, simple closed curve, oriented counterclockwise. Orientation, very important. Let F equal PQ be a vector field with component functions that have continuous partial derivatives on D. Then the circulation along partial D, the boundary of D, of F. Why is that a capital R? Is the double integral over D partial Q partial X minus partial P partial Y. So Green's theorem allows us to write circulation of a vector field as a double integral. Does Green's theorem violate the fundamental theorem of line integrals?
It's not something like an application of the fundamental theorem of line integrals? No? The fundamental theorem of line integrals, you have your capital F, you get a partial from that, right? And then it's the difference between what that partial gives you at one end from the other end, right?
Partial. Referring to potential?
I'm sorry, potential.
Fundamental theorem of line integrals for what type of vector fields?
Conservative?
What is the circulation of a conservative vector field?
0.
So if F is conservative, is that double integral 0?
Should be.
Why?
Because taking the integral of 0 is still 0.
Why is the double integral? Why is what you're taking the integral of 0 though?
I'm sorry, repeat that again here.
So why is the integrand 0?
I don't know.
That's what it brings What does it mean for the field to be conservative?
The partial of the second term with respect to x minus the partial of the first term to y equals 0, or they're the same.
Well, that is definitely true. That is a way of saying it. Mixed partials are equal. Remember, to be conservative, partial q, partial x has to equal partial p, partial y.
No curl. It's the same thing, right?
Well, you don't really do curl of a two-dimensional field.
Okay, that makes sense.
So this is just mixed partials are equal,
Okay,
which means their difference is 0. So yeah, you're integrating 0, which is 0.
right.
Good. Green's theorem does not violate fundamental theorem of line integrals. If it did, then either Green's theorem is wrong or fundamental theorem of line integrals is wrong.
There's no sign sheet.
Yes, there is. You don't see it?
No, there's nothing there.
Well, you might need another prescription then.
There's literally nothing on the door.
There's literally something on the door.
Gaslighting doesn't exist.
Amazing.
There's literally something there.
Ah,
You always do that.
well, I'm just not signing it today.
Technically, there are millions of somethings there. So we are going to verify Green's theorem. That would be the boundary of our region, right?
May I ask a question? You certainly already covered this. Why are we writing that as partial of D?
That's what it means. That means boundary of
Okay,
the region.
okay. All right, thank you.
And so you see it two ways, either it's written as C or, if you want to be more explicit, boundary of D.
Okay, all right, thank you.
What's the orientation?
Counterclockwise.
So starting on that bottom curve, which direction are we going? That direction. Rightwards or leftwards?
Rightwards.
Which means that top curve we're doing what?
Going leftwards.
So we'll just draw those arrows there as well. Now that point's easy. What's this point here?
1. 1.
So again, that's fairly simple. So we have to do two things. We have to evaluate the line integral to the circulation, and we have to evaluate the double integral, and then show that they're equal. What's our vector field?
Is it xy plus y squared and then x squared?
Pay attention to your differentials. Because I don't always have to write it that way. I could do dy and then
Right.
plus dx.
Right.
So you have to pay attention. Which means P is what and Q is what. I'll just write those out as well. For Green's theorem, what's P
xy plus y squared,
and what is Q?
x squared.
So let's start by doing the line integral. To evaluate a line integral, what do we need to do?
Do we have to parameterize our region,
Region?
our the bounds of our region, the thing that defines our region? Do we have to take y equals x and y equals x squared and parameterize that so we're only talking about one variable?
I don't know why I talk about a region.
Question, why is that the vector field? I don't follow.
What's dr? How could you write the differential for r?
I don't know.
What does dr represent? Differential for position vector, right?
I don't remember.
Area?
So position. So you have a position vector, 2 dimensional, let's say.
Okay.
How is it written?
It would be a vector value function with 2 parts, right?
What does the first component represent?
The x position,
What about the second component?
the y position.
So wouldn't dr just be the vector with components dx, dy?
Okay.
Now take those dot products.
All right. What is f1 and f2 in this situation? Oh, that x squared isn't attached to the dx?
No.
Oh, okay. That would explain why I was confused. All right.
It's just another way of writing the integral of a line integral, and it's typically what we see with Green's theorem. We have to parameterize something, I agree.
And we're not parameterizing the y equals x and y equals x squared business?
We might be.
Okay. But I'm not really, but I'm missing what that means exactly.
What do the x and the x squared represent? The boundary of the region, I agree. In terms of line integrals, you're not parameterizing a region. You're parameterizing a path.
Okay. That path being what we have in pink here, right? Okay.
We're not going to parameterize the region.
Right.
It's just the boundary that we want to parameterize, the
Yeah.
path itself.
Yeah. Okay.
What do you notice about that path?
It returns to where it starts.
Well, that's definition of circulation. What else do you notice?
It can, I don't know if this has anything to do with anything. It can be represented as either vertically or horizontally simple.
Path can't be vertically simple or horizontally simple. It's just a path.
Oh, right. It's the path. It's the path.
You're still stuck on the region.
Yeah, yeah. Gotta get through that.
It's actually really obvious.
We're trying to notice something about the path, right?
Yes.
That word starts and ends. It starts at 0, 0, and that's what
What starts at 0, 0 and ends at 1, 1?
like the two endpoints of the path.
Oh dear, no. Only one path has an endpoint at 0, 0, and, or endpoint at 1, 1 and starting at 0, 0. This is the union of two non-overlapping paths. This can be broken into two paths. So two line integrals. That's the obvious part that you're missing. This is where direction matters. First path goes from 0, 0 to 1, 1. Second path goes from 1, 1 to 0, 0.
Does it have to be done like that?
Hmm?
Does it have to be done like that?
No, you can start and end at any point. But, depending on where you choose your starting and ending points, you may have more than two paths. Which just makes it worse. This is probably the easiest way to do it. Let's call that bottom path C1. Parameterize it.
So R of t equals t and t squared. And it goes from 0 to 1.
Parameterize that second path.
t from 0 to 1. Oh,
Wrong direction.
yeah, it's crucial. Crucial.
So I don't want to use that.
Okay.
I want to stick with t going from 0 to 1. So find a parameterization using that.
We should put the negative up front, don't we? Because we're flipping the, you can't just stick a negative. Because we're flipping it.
So 1 minus t.
1 minus t.
Minus t. 1 minus t, 1 minus t is.
What you do is you subtract the line integral from that using that parameterization because it's the opposite direction.
Okay.
Because if you did the negative, then that's saying that you're starting at 0 and ending at -1, which is clearly not what this path does.
So, you are subtracting from the upper, like, 1 minus t, not 1 minus t, because you're subtracting t from what exactly?
Because we start at 1 and go down to 0
Okay.
for x. So 1 minus t would satisfy that, right? And y equals x. So that's how you get your second component.
Yeah.
Again, you could use t 0 to 1, but just remember it would then be integral along c1 minus integral along c2 because it's the opposite direction.
Right. And these are the bounds. That's the bounds you'd wind up with if you did the textbook second point minus first point, right? And work out the parameterization from that.
What do you mean?
Well, so you're going from 1 1 to 0 0. So like, all right. So you have this vector -1 -1. So then if you go through the exercise of saying x equals x initial 1 plus negative.
Oh, you're trying to parameterize the line.
Yeah, that's what you
Using
wind
that
up with.
method. Yeah,
Yeah.
you could do that.
If you were inclined to go through
You
all
could
that.
do that, yeah.
All right, that's what you okay.
More work.
Right.
Work than you need to.
Right. That's what I'm used to.
Evaluate your vector field along the parameterization.
There's two paths, are we gonna do it for which set of parameterization?
This is for R1, first one.
Okay.
Well-
T cubed plus t squared, t squared, no, t4, t cubed plus t to the 4, t squared.
number that gets dotted with r prime.
Which is 1, 2, 2.
dt. Now do the same thing except now r2.
Is it just 2 t's? 2t squared t squared. Oh, it's 1 minus t.
What's r prime? There you go. Now we have to do that. Form that dot product. For the first one, that's what? T to the 4th plus 3t cubed? You perform the second dot product. There's our setup for the line integral. Now evaluate it. Minus -1 minus t quantity cubed from 0 to 1. Just -1. -120. Now the double integral. We need to describe our region. How would you describe that region?
Well, as being bound below by y equals x squared and bound above by y equals x. So you could say like x goes from 0 to 1 and y goes from x to x squared. From 0 to, wait a second. Y goes from x squared to x. Right.
Partial Q, partial X.
2x.
Partial P, partial Y.
X plus 2.
X plus 2y minus 2x is 2y minus x. Except I think I did the order wrong, did I? Yeah, I did. It's q minus x minus 2y. dy dx. There's the setup. Now the evaluation. Well, x, from x squared to x, remember it's dy. Right, so it's going to be x times that length. X squared minus x cubed. Minus the quantity y squared from x squared to x. And they go from 0 to 1. X squared minus x squared is gone. That's what we're left with, x to the fourth minus x cubed. One-fifth minus a quarter. Which is what?
Negative 1/20.
Are they the same? Green standards are verified. Are you serious?
And could you just remind us again, just to trying to get good grasp on this. Just looking at that first part there, how would you read that? Like, that's asking you for the line integral, right? Of the
vector field xy plus y squared, comma x squared.
comma x squared. Okay, it's asking you for that line integral. All right.
And this is the same as this.
Mhm.
They're the same.
Okay. If you were reading that in your head, would the partial the
Circulation along the boundary of D.
okay circulation? All right, thank you. Circulation along the boundary of D of that function
Of the vector field
Of that.
xy plus y squared.
of that
X
vector
squared.
field. Okay, thank you.
Uh-oh. What happened here? Let's take a look at this path. Squared. X goes from 0 to 2, y goes from 0 to 1. Let's leave the axis, why not? There's the path. It's the first thing you notice. first thing you notice about that path?
It's curved. Looks like it goes to a certain-
More important than that.
Doesn't actually look like a closed path at all.
Doesn't look like.
No.
It doesn't look like it because it isn't.
I wasn't sure. Maybe it was just wasn't the right scale.
No, I did the scale purposely.
Okay.
Right, look, we go from 0, 0 to 2, 1. So x goes from 0 to 2, and y is going to go from 0 to 1. So that's why I just did this little bit here. Yeah, that's not closed. That means Green's theorem can't be used. So we have to parameterize that path. Oh boy. What do we? Do you notice anything about the vector field?
Will this involve finding a potential?
Come on. If we found a potential, what would that mean?
I haven't thought that far ahead.
Oh dear.
All right, I know.
What kind of fields have a potential?
Conservative vector fields.
Is that conservative?
It doesn't. I would guess it's not. Or wait a second. I don't know.
Yeah.
That's conservative.
How do you know? How did you figure that out like that?
The partial of the dx term with respect to y is minus 6 xy squared.
Okay.
And if you do it with the other one, it's
Okay.
also minus 6 xy squared.
All right. Cool.
Why is that important? Or I should say, why is that useful?
If f is conservative, then the closed integral,
Fortunately, it's not circulation. But there is something else in that theorem. That integral's path independent.
Does that mean you don't have to worry about what's happening between endpoints?
use that path. Isn't that a lot easier? You could find a potential, but I find just doing the straight line in this case is actually easier.
Yeah.
Parameterize that.
Two TET. T's 0, 1.
Let me hang. Can't just give
I
you.
was making
Parameterization
sure.
always includes a domain.
Yeah.
What is the field evaluated along the path?
One 160 T to the 4. Is that the start point?
Keep going.
Minus 4 T to the 4.
Is that simplified?
No. 160. 156 T to the 4. Oh, minus 12 T to the 4.
What's R prime?
2 to the 4.
What is that dot product?
300 T to the 4.
Oh, that is sexy. That just equals 60.
So what we just found was the line integral across that field along
Well, the line integral through that field,
through that field along the
along
path
the path.
defined by that parameterization.
Well, technically it was this one, the black.
But
But because of path independence, the path that we take doesn't matter.
right. Okay.
So that's the work done
Right.
in
Work
moving a
done.
particle along any path from that starting point to that ending point
Right.
through that force field.
Okay. Now I keep trying to figure out some way to like visualize, if there is a way, what that 60 represents. Like
Work.
work.
So
All right.
if we use SI units, it took 60 joules
60. Okay.
to go through that force field.
And if the force field was like if the force field.
So I guess one of the best ways I guess I could describe it is you're walking in like a heavy rainstorm.
Right.
You have a force field, the velocity field.
Right.
How much work are you doing going through, like from a certain path.
Right.
So like from your front door to the car, from the car to the front door through that windstorm.
Right.
How much energy you're exerting doing that. That would be what we just calculated.
Okay. Now, if your force field,
And that works really well because if it's raining, you can actually see,
right,
you can kind of visualize the force field of the wind.
yeah, and if like your force field was like a bumpy surface, right, like something with,
Well, force field wouldn't be a bumpy surface.
well, if you represented, oh man, well, anywhere you go on that XY, you get a value, right,
A vector.
a vector. All right, I was just trying to get used to it.
It's force field is not really a surface.
All right,
It's a field that
Right.
you're going through.
right. I'm just trying to find some way of like
Or if you like the gravity field,
right,
it's not a surface, right? It's just a field. Earth's magnetic field.
right,
It's not really a surface per se.
yeah. So you can't. So there's no way to
It's
like.
a field.
So there's no way, like when we learned integral underneath this line, there's nothing like that for this, is there?
Because we can actually use line integrals to find area.
Right.
It's found right here.
All right.
Show that the area bounded by a simple closed curve C is given by 1/2 the circulation of x dy minus y dx. So let C be a simple closed curve that encloses a region D. That is, C is the boundary of D. We can use green stamp. Then this would be true, right? Simplify down to just 2dA. Half times 2 is 1, right? What does that double integral represent? Area of what?
Area. Is it the area of the vector field bounded by? Is it the?
precisely what we wanted. Which now makes finding the area of an ellipse really simple. What are the limits of integration for this shape, this curve?
Negative beta A.
And negative b to b.
You have to figure it out. You have to know how the formula for an ellipse works, right?
0.
I agree with 0.
2 pi.
Yes. 0 to pi. Parameter is theta, right? The radius doesn't matter. 0 to 2 pi. Or pi to 3 pi, right? Or negative pi to pi. Something along those lines where you're going a full. Let's have enough of the nonsense. Vector field evaluated along the curve.
So negative A sine theta, comma, B cosine theta.
How'd you get that?
Differentiating R beta,
Why are you differentiating?
because we have,
I don't want dr yet.
oh, that would be the dr.
That's what we thought would, yes. So that I agree once we get there. I want, what is the vector field evaluated along the curve?
Negative b sine theta, a cosine theta. Oh,
That gets dotted with negative a sine and cosine. theta. That's what? AB sine squared.
Theta plus AB cosine squared theta.
Which equals what?
AB integral 1/2 times the integral from 0 to 2 pi of AB. With respect to theta.
You're right, 1/2. I was jumping the gun. Theta.
And then pi AB.
Here's your area of an ellipse. Pi times A times B.
You know, there's no formula for the perimeter of an ellipse other than an infinite series.
Yeah, I believe that. Although, I thought I did see it. I'm gonna look that up. These are sexy. There's an approximation. There's an approximation.
Yeah, and the
There's an approximation. I like this one
Rock
because
fusion
this is
like 1,000 times better than rock fusion.
because the dude was an absolute genius.
Yeah.
Oh look, he actually came out with both of those.
And then now I think number 3 is like another 1,000 times better than the second one. But it's more complicated.
There's the actual formula. It is an infinite sum. Or that one. Ooh, that one's awesome. Oh, that's really cool. Using binomial number. Ooh! Binomials with half integers. Oh, that's really awesome. And or the perfect formula, which I disagree with. That is not the perfect formula. Oh wait, that's right. We just did area. Yeah, I would agree with that. Perimeter would just be the line integral of the parameterization of the, or circulation of the parameterization r theta, d theta.
Using lowercase e as a variable should be illegal.
Why?
Because e is always like Euler's number.
Technically, Blackboard is Euler's number.
What was that? Blackboard what?
I need to add no screen share. Added. No, wait. that's good enough. Yep. Okay, that was the right one. Huh. You don't do lowercase a, really? That's actually annoying. It is actually really annoying. So it'd be very similar to the Blackboard bold R.
Oh,
Has that extra, it just has an extra line. That is technically what we should be using for Euler's number E. We also sometimes use EXP of
Yeah.
1. But that's where context matters.
you could say E if you just.
Because I could
have
say,
no-
I could say we shouldn't be allowed to use little p either. Because little p has a meaning. So does little h.
I guess, but like E is like really well known, right?
So is h. So that's your study quantum mechanics. So is little p if you study statistics. True.
Math notation is all ridiculous anyway.
Huh?
Math notation is all ridiculous anyway.
No, it's not.
Well,
Math notation makes perfect sense.
the first discussion question, like the dude who wrote that paper, he apparently wrote a book on the history of math notation and how it was all just kind of made up along the way.
Well, no kidding, it's made up.
Yeah, but how like it's
So
completely
is
arbitrary.
5.
Yes. So
5
it's
is just
fine.
made up.
But I mean, like it's all completely arbitrary.
Technically, all of math that you know of is made up. We just made it up to explain the universe.
Clearly, I'm doing a poor job of explaining this.
So you're not wrong. It is made up. You know, and they just came up with notation. It's just whatever they used. And then they ran out of Latin letters and Greek letters. And we didn't want to have to go back to ancient times to use hieroglyphics.
Wingdings.
Why not? Those were kind of cool. Start drawing birds.
You think they might gonna start moving to Norse ruins?
I can get behind that.
Well, then we have to rewrite math. So probably not. After you tried to derail me from that on that tangent, the perimeter. Ooh, actually, I have a fun assignment for you. Derive that infinite series formula for the perimeter of an ellipse.
I'll work on it.
And Dave can fully explain it. That's why I'm a math major. Don't even know how to spell. Hell, I don't even know how to count. I don't even know how to tell you how to count. So what do you notice?
C is the union of 3 different lines.
True? Something even more important. I guess there's 2 things that are really important.
You can describe inside
What region?
the region bounded by path.
So how would you say that? C is what?
C is the border.
Oh, you're so close.
Yes,
Boundary.
C is the boundary. Right, different thing. C is the boundary of.
C acts as the boundary of a region. What else do you notice about C?
It's going counterclockwise.
And it's oriented counterclockwise. Green's theorem. So, yeah, we don't have to worry about that 3 non-intersecting paths bull crap. Because we can just treat this as a double integral. Yay! There are 3 things we need to find. First, we need to describe the region that's being enclosed.
X goes from 0 to pi over 2, and Y goes from Y goes from 0 to 2x over pi.
What are we taking partial x of?
Y. I mean Q.
What's q?
Q is cosine x.
What is it?
That is negative sine of x.
And what do we have to take partial y of?
P, which is y minus sine of x.
What is it?
It's 1.
What is it? Negative sine x minus 1. So there's the application of Green's theorem. Next comes setting up the double integral to evaluate it. Factor out negative 1. That would be the double integral setup, right? How would you evaluate that integral?
Integration by parts.
That'd be broken up into 2 integrals. First one requires integration by parts. Second one is easy. I'll leave you to do integration by parts.
Is that not what you're doing?
And use formula number 37. Which, if I was evil enough on the exam to say, no, I'll use an integration aid, you have to do integration by parts. So you have to show me the work by hand. Depends on how badly I want to write up the solution. All right, so now it's just a matter of evaluating that. Sine of pi over 2. Cosine of pi over 2.
0.
Okay, that's gone. Oh, look, and that's 0. That whole thing is 0. First time we figured it's just 2 over pi, right? Second one. Plus pi squared over 4 divided by pi is what? And then it's 0, 0, there's your line integral. Which is a hell of a lot easier than if you tried to evaluate it directly. Right, with the union of 3 paths. Granted, the paths themselves aren't that difficult. Right, they're fairly straightforward. In fact, I think I'll let you do that path integral directly over Thanksgiving. That'd be my Thanksgiving gift to you.
Is that example 3?
You can just evaluate that
Question
line
5.
integral. And evaluate that line integral directly. You can even do it while the turkey's cooking.
Yeah.
I'll just cover past this space and never come back.
Huh?
I'll just cover past the space and never come back.
I'll end up with a burnt turkey.
And if you never come back, that makes my job easier. one less grade I have to input. Yeah, your turkey shouldn't burn. I mean, unless you have a really tiny ass turkey.
And it
Standard turkey takes what?
Don't ask
6
me.
hours?
Yeah.
Well, it depends on the
I know it's I know you have to cook it a certain amount per pound. I forget what that is. I think it winds up being like 6 hours or something
I don't know. I'm sure
for a standard sized turkey.
It depends on how you prep it.
studies have been done.
Prepping doesn't matter.
No, I mean like stuffing, gravy.
That also doesn't matter.
What?
The turkey's going to take the same amount of time to cook regardless. You just have to remove the stuffing midway through because the stuffing's going to cook a lot faster than the turkey does.
Oh, just what I know about American culture.
And then you make the gravy after the turkey's finished cooking. Because you use the wonderful turkey juices. I like to cook. If you really want to make a great turkey, you put in a bunch of aromatics.
Like herbs and stuff.
Oh yeah, what you do is you set the turkey on a rack, and under the rack you put in a bunch of aromatics and water.
That's cool.
Onion, celery, put in a bunch of herbs, and then what you can do is use, when the turkey's finished cooking, use that leftover aromatics in the stuffing.
It's a good system. good. It's a good thing.
Just don't have the time to do it all the time. A lot of prep, because that is a lot of prep to do it that way.
Yeah.
So if I'm actually cooking Thanksgiving dinner, I'm probably up at 6 in the morning,
Man,
just to start the prep.
it's a full day.
Because I want the turkey in, so it takes about 6 hours. Figure you eat about 3. So when do you want the bird in?
Man.
You're
Yeah.
done at 3. Well, 8 hours, 7 to 3. So it has to be in by 9.
It's a full shift.
Turkey has to be in by 9.
Uh,
Oh, and then you also have to let it rest.
Man,
So I actually probably put the turkey in around 8:30.
you gotta deal with the guests. You gotta cater for everybody.
Yes.
Right.
I was talking about my dinner.
Right.
Damn everyone else.
Yeah, they can heat up a pizza.
And then you have to time everything perfectly so that you get all of your sides done at the exact same time. Obviously, make the stuffing ahead of time. You add the aromatics afterwards. You can make the gravy as the turkey's resting. By the time the gravy's done, the turkey will finish resting.
It's an operation.
Question on green stamp. I should make you find the surface area of the turkey using calculus.
Find a function.
Find the parameterization of your turkey, but calculate the surface area. And then make you calculate the time too.
Let's say a cube is close enough to a turkey, I think.
Not even close. Not even close, because the turkey has a lot of empty spaces.
Ah, man.
Put a lemon with it, like use that lemon with the turkey.
Use what?
Lemon juice.
Just grow it like one of those square
No,
watermelons.
not with turkey, I don't
Even
use lemon.
watermelons, where you just put the
I'll
turkey
use lemons and limes with
or
ham.
something.
My mom used it to cook with like
Lemon and lime juice over the ham, and then pat it down with brown sugar.
what about beef Wellington?
And then pineapple rings and cherries. Make it all together.
Beef Wellington?
Don't have time to make a beef Wellington. But that, you wouldn't have beef Wellington for Thanksgiving or Christmas. You have that for fancy. Because they're expensive to make too. They're not cheap. You got 2 things due today. You have a quiz due, that's right, quiz due Thanksgiving at 5. So I recommend you do that before you eat dinner. See, you can do that while cooking the turkey.
That's great.
I mean, you have to wait for the turkey anyway, so
No, I haven't eaten
It's something to do.
meals for weeks.
you also have homework due on the 28th at the end of the day.
I assume.
Great, December 23rd, what the hell?
Yeah.
Why is that December?
Should we be fully prepared to work with Green Serum for the quiz?
No, the quiz went live last week, right?
Yes.
No.
Okay. Okay. All right. Cool.